Good morning. So, a system is not a tree. That's a bold assertion. I want to talk about structure. Structure in the abstract sense, because that is what software is, structure in the abstract sense. It's not concrete in the way that most things are in a real world sense, and indeed it's not living in the way that something like a tree is. The question is, what is it that we do when we organize stuff? If you like, a software system is organized thought. It is executable fiction. It's stuff that we make up, but we give it some kind of structure. It's not just arbitrary. Well, actually, you may have worked on a system where it feels kind of arbitrary. But it's not supposed to be arbitrary. It's supposed to have some kind of discernible order to it. It's supposed to be comprehensible. It's supposed to be a reflection of the thought stuff, but with a little bit of consideration. And so I want to go through what we mean by, when we say a system is a tree, and then look at what we mean by, well, a system is not a tree. What does that actually mean in terms of how we code and how we reason about systems? It would help if I turn that one on. There you go, the power of on. There you go, brilliant. Let me think, why have I put this here? I put this here because my name's on the cover of them. I put this here also because it happens to summarize a couple of areas of interest of mine, and one of the aspects of patterns will come up later. Architecture we think of as being the gross structure of a system. There's a bit more to it than that, but there is this idea of this large concept of the system. And then we break it down, and we break it down all the way to the stuff that we talk about when we talk about programming. And I'm one of those people who actually quite likes the word programmer. Software developer seems far too many syllables, and if you shorten it to developer, then you can get into those interesting conversations with people. What do you do? I'm a developer. Oh, yeah, my partner's in real estate as well. And that's not really a group of people I want to be associated with. I want to be associated with people who do programs, okay? I'm sure they're lovely people. No, I'm not. I can't do this on a Tuesday. I'm going to be candid and honest. And so, therefore, I think that we should be quite honest. The act is programming. Programming is not merely the act of coding. It is also the act of everything else to do with it. It is the thought, it is the overall architecture, it is the understanding of requirements, it's working with other people, and so on. And all of these things connect to create a structure. And what kinds of structures do we like to use? And what do we prefer and refer to? So I'm going to quote from Fred Brooks' The Mythical Man Month, where he makes a particular observation about how we spend our time. And the first observation he makes, he goes back to Aristotle. Let us examine software's difficulties. Following Aristotle, I divide them into essence, the difficulties inherent in the nature of software. To be precise, the difficulties inherent in the nature of the domain that you are trying to work in. And accidents. Those difficulties that today attend its production, but that are not inherent. In other words, the things that are not intrinsically a part of the software development that you're doing, that are not intrinsically to do with whatever domain that you're working in. And then the question, to which I think we probably know the answer, unfortunately. How much of what software engineers now do is still devoted to the accidental as opposed to the essential? How much is to do with byproducts of just the way we have designed something, just because we've chosen something in a particular way? Now, I was doing a consultancy visit last week to a company, and I saw a couple of their, four of their projects. And I've been doing stuff for these guys for a number of years. So there's a lot of continuity there. And one particular group, It's not that I kind of hit my head against the wall every time I see them, or burst out into uncontrollable tears or anything like that, or run fleeing from the building. But it is one of those things that a few years ago I gave them two recommendations for how they should consider their architecture. And I said, the first one, you've got 12 months, you said, to develop this. If you take the first recommendation, it's kind of like a sort of dungeon game, isn't it? If you take the first door, it will take you 3 months. If you take the second door, it will take you 6 weeks. and then you can go on holiday for the rest of the year. But if you choose the door of darkness, as your current estimates and architecture suggest, it will take you 12 months. No, it won't. It'll take you 18 months. They chose the third door. And so every time I go back, in fact, last week was very easy, because I said, didn't I tell you guys this last year? Didn't the problem that you had last year, couldn't you have solved? And it's a little bit like that. So for that team, I can say pretty much everything they have done since 2011 has been to do with the accidents. Now, not all teams are as extreme as that. I saw a couple of really good teams last week. But there is this question of being able to see the structure, to see the trees for the wood, so to speak. Now, you know, pop reference, Michael Jackson. Okay, not that Michael Jackson, a different one. Software requirements and specifications. Now, this book is a truly brilliant book, and only a few people know this. It's 20 years old now, and it's kind of a best-kept secret. It's really worth a read. Okay, it doesn't have the most riveting title, Software Requirements and Specifications. It's not kind of, you know, requirements distilled or something like that. It's nothing sexy in there, or no requirements, or no specifications, or anything like that. It's got no hashtag that makes it interesting. But there's a mild suggestion in the subtitle, a lexicon of practice, principles, and prejudices, that he's kind of got some interesting things going on here. And in here, he looks alphabetically, you know, through all the way from A through to, I think he gets about as far as W or Y, a number of little items. And near the beginning of the book, because it begins with A, he talks about arboricide, which is not a common word. Arboricide is the murder of trees. Okay, so I'm not trying to guilt trip you here on any kind of environmental thing. It's more specific. The victims of arboricide are the descriptive tree structures that are so often found in software, holding together many individual elements in one coherent and immediately understandable harmony. In other words, it all kind of fits together, this beautiful hierarchy. Software development should not be a trade of constructing difficulty from simplicity. If you want to take any quotes from this talk, I think that one is the one that you want to have like pinned somewhere. Quite the contrary. So where there are trees to be shown, you should show them and refrain from turning the relationships they describe into a puzzle. It is essentially a matter of the span of description. Arboricide then is using a smaller description span when a larger one would be better. In other words, size your description structures, and software as a description structure, it is information, to the things that make sense, can be understood, can be manipulated, and reflect aspects of the real world. Fine, we see that. More briefly, Donald Knuth, trees sprout up just about everywhere in computer science. We have this idea, this familiarity, because we know that trees are a real thing. We know that trees have the roots at the top and the leaves at the bottom. And all those other people out there who have this other belief about them are sadly mistaken, but we humor them. And we know trees are red and black, not green. So what's one of the most common sources of trees? Let's go back a bit. Structured programming. Structured programming. A number of people have an idea of what this means, and we can summarize it nicely as block structure. There's this idea of hierarchy of calls, decompose a system into a recursive whole, a tree. So this is kind of good. And we end up with kind of a main program and subroutine kind of approach. Okay, you have main, it calls subroutines, which call further subroutines, and so on. Now, what a lot of people don't know is actually there is a little bit more to this. There is actually an architectural model that fits with structured programming with its own jargon, an afferent branch, a transform branch, and an efferent branch. So feel free to use that with your colleagues at any point. And you might be thinking, well, you know, hey, we don't use main and subroutines and stuff like that. We're all kind of functional now. That's OK. There you go. Functional programming. Done. Structured programming and functional programming, the difference is degree of side effects. It turns out the decomposition criteria are very surprisingly similar. And we have this overall structure. And this looks beautiful, and it's pretty, and it's tree-like. There's only one problem. It's not the way that we program, not even when we try to program like this. We end up with the fact that the graph is compromised. It becomes a directed acyclic graph. In other words, we like relationship that fan in as well as those that fan out. We like reuse relationships. We mix levels quite naturally. In fact, sometimes we recurse levels quite naturally. We describe something in terms of itself, and this comes out as a very natural description. So it's kind of tree-like, but if you ever saw a tree like this in a forest, you'd wonder what on earth had gone wrong. You know, this is a serious case of arboreal engineering. This is no longer a tree, but it is certainly very useful. It's a better reflection of how we think. So the tree was a kind of useful starting point, but it's sort of fallen apart. It's become deconstructed into something else. Now, we might think, well, okay, that's all very well. This is, you know, I might apply this kind of reasoning to structured programming, functional programming, procedural thinking, and so on. But surely we should be more up to date and talk about, you know, some object-y stuff as well, because that's where people often find trees. It turns out object-oriented programming was covered in this book from the 1970s. Concept hierarchies. They didn't call it inheritance. It's called concatenation. Concept hierarchies. The construction principle involved is best called abstraction. We concentrate on features common to many phenomena, and we abstract away features too far removed from the conceptual level at which we are working. So everything that you need to know was invented in the 1960s and 1970s, including disco, unfortunately, but there we go. So there's a different tree. And this is very similar to one that I've come across in a couple of companies, but there's one specific incident I'm thinking of where a company had created, they had a team that had created an architecture for middleware. It was based very much on these lines. They created an infrastructure level, very much a kind of toolkit of classes and base classes there, and they derived from those a set of service-related classes that would build on this idea of toolkits. This is a very common idea of having the root of the hierarchy gift all of these wonderful services, and you accumulate these by concatenation as you go down. And finally, you hit your domain model, and your application programmers busily hack out this. So the top two levels were communicated and developed by a core infrastructure team, and then the application developers worked in the domain. The problem is that this was an absolute nightmare to develop against. The dependencies were huge. You looked at the service layer, and you looked at the infrastructure layer, and they brought in dependencies from way, way over there and way over there in order to try and test the domain classes. A ridiculous amount of work had to be put in. And any kind of change was a ridiculous amount of change. It kind of let off a kind of tsunami of a ripple effect every time you tried to change anything. It actively resisted the one thing that we know is true in software development, that change is the only constant. So I made myself desperately unpopular. I was actually supposed to be there reviewing their test cases. And it turns out that none of the application developers could successfully develop any tests against this. I remember the first moment I sat down next to one guy, and we're looking at this test case. And it's just one of those things. You kind of ask, you say, just out of interest, the color of the code, yes. That's exactly the same color as the color of comments. Yes, it is. Is that because it's a comment? Yes, it is. I had to comment all the tests out. So we're looking at a big comment that runs. Well, we never execute it because it's a comment. Well, yeah, that stands to reason. So why is it commented out? Because we can't get the test to work. Oh, okay. Well, perhaps we shouldn't just review a comment. And this was pretty much repeated in various forms around the other developers. So kind of spending a bit of time with them, worked out that what they really wanted was something like this. And here we make an additional separation. So what you see here is, rather than one big tree structure, we see multiple small tree structures that are bound together. But what we've done is we've further separated concept from realization. Rather than using inheritance as a subclassing mechanism, we've used it as a classification mechanism, an original concept approach, and then plugged in various pieces. We still have the cross-cutting view of domain, services, and infrastructure, but now what we see is that our model is, well, we no longer have a tree, we have multiple trees that are linked together. I guess you could call it a forest or a copse or something like that. And then our classification model cuts right across itself. We have concept realization, domain services, and infrastructure. It's no longer tidy and nested and tree-like, but it turns out to be surprisingly useful. So, if anybody's wondering, one of my hobbies is taking photographs of books. I've got quite good at it recently. This is a rather unusual book. As you can tell from the cover, this is actually a book about postmodernism. Postmodernism is a fancy way of saying, we couldn't be bothered. So, hey, here it is. That might be a gross oversimplification, but it'll do for this talk. There are some interesting things in here. The thing that I want to focus on is it's a collection of essays about really looking at the idea of design after a strict, tidy world view that perhaps some aspects of modernism sort of pushed, but not necessarily all of them. So it caricatures modernism a little bit, just as I've caricatured postmodernism. The essay I want to focus on is this one, A City is Not a Tree. This is the one this talk takes the title from. A City is Not a Tree by Christopher Alexander. And if you're thinking, perhaps that name sounds a little bit familiar, it should do, because on the very same floor, but on a different day, I took this photograph. The Timeless Way of Building, this is one of the classic books on patterns, not patterns to do with object-oriented design or software development, but original patterns, patterns to do with building architecture. And Christopher Alexander was the originator of this. So it's that Christopher Alexander. And again, he's concerned with large-scale structure and small-scale structure. And so in A City is Not a Tree, he makes a number of observations. One of the sort of key observations, the tree of my title is not a green tree with leaves, it's the name of an abstract structure. So we're all comfortable with that, that's great. He's just speaking to building architects who think that trees are green and stuff like that. I shall contrast it with another more complex abstract structure called a semi-lattice. Both the tree and the semi-lattice are ways of thinking about how a large collection of many small systems goes to make up a large and complex system. So if we imagine something like this could be an organizational chart, an organogram. It could be a call chart. It could be a number of different things, but it has this kind of common idea of a strict tree structure. And it's neat and tidy, and certainly if it's an organizational chart, it's normally neat and tidy and represents power struggles, but it doesn't actually represent how the work is done. The semi-lattice is potentially a much more complex and subtle structure than a tree. The subtlety is important, but it's the complexity that people fear. In other words, normally when things are not organized and tidy, the complexity is accidental rather than essential. But to go a step further, he says actually there's something missing if we don't appreciate the right kind of, as it were, inherent or essential complexity here. It's this lack of structural complexity characteristic of trees which is crippling our concepts of the city. What he was looking at was the idea that sometimes people were trying to do urban planning based on a beautiful tree model. In other words, you kind of make everything nested and you have your kind of industrial region, semi-light industry, residential, and so on, and you zone it like that. You have very strict hierarchical structures, and you also have a tree structure in terms of how the roads feed everything. And it's all simple. It looks brilliant on a slide. It looks brilliant when drawn out. Absolutely a hell to live in. He says the reality of today's social structure is thick with overlap. The systems of friends and acquaintances form a semi-lattice, not a tree. Now, why is this relevant? It's relevant because when we go back to this and we appreciate how organizations actually work, then they work like this. Nobody puts that on a diagram. The fact that actually, my kid's in the same class as the other kid from over there, and that person is further up the organizational tree, and we go to barbecues together or do something like that. The fact that I've known that person since university, or the fact is that I get on really well with that person because we worked on a project a while back, and although we're in different parts of the organization, we still communicate about related work, and actually that's how this project got done. In other words, it's the subtlety that actually gives rise to the reality. It's not done like this, it's actually done like this. Now, why does this matter? Because organizations, large and small, have an effect on their software. This is not the resolution of my screen. That's causing this. This is the sheer age of the pixels we're dealing with. Okay? These pixels date back to a time, way before Neil Armstrong and Buzz Aldrin set foot on the moon. This was ink. This ink was laid down before even 2001: A Space Odyssey had previewed what it would be like to land on the moon. It was written in 1967, published in 1968. It was an observation about how systems and people interact. It's often known, this is Conway's classic paper, published in Datamation in 1968. Melvin Conway, How Do Committees Invent? From which we get the idea of Conway's law. It turns out to have a really, really strong effect. The basic thesis is that organizations which design systems are constrained to produce designs which are copies of the communication structures of these organizations. Not copies of the organizational chart, but copies of how people actually get together and do things. It's not even necessarily just geographical, it's lines of communication, which there are many forces on this, and you kind of see these forces pushing and pulling against a code base. It also explains to us why it is that sometimes, as his next observation says, we have seen that this fact has important implications for the management of system design. Design efforts should be organized according to the need for communication. But so here's a very simple question. How do you make a system big? How do you make a big system? What determines the size of a system? And lots of people would love to say, oh, the size of the system is determined by the amount of functionality that we need to have in it. That's beautiful. Pinch them, wake them up, because that's not reality. They're in a dream world. It's determined by the number of people we decided were going to be involved. Okay? It turns out that you can make a system. In fact, an example of a company I did some consultancy for a few years ago. They were creating this kind of state machine, it's a telephony system. They're creating this state machine, and it was beginning to look really, really complex. They were taking a very C-based approach. In fact, it was a really ugly C-based approach. You could have done it more elegantly if you'd programmed C properly. But they were using C++, and I said, look, here's a bunch of techniques that will simplify this. And I drew them up, and I said, look, see how simple this is? And I did a simple demo of code. I said, and this will scale really nicely. And the next day, I went in, and they'd had the little Scrum meeting, and I said, so how's that going? And I talked to the one guy that I thought was going to be responsible for the state machine. He says, yeah, we've got no problem with that. We think your idea is great, and the 8 of us are now going to develop it. So it's like, no, this is a 1- or 2-person job. It's a 1-person job, or rather it's a 1-keyboard job. And at this point, mob programming had not been invented. Pair programming certainly had, and these teams did pair, and I just thought, you need 1 pair to sit there and code this up. You'll be done by the end of the week. Oh no, when you've got 8 people, you can take months to do this. Because this team, there were other teams, this team was the state machine team. That's what we do. So therefore, that's what we're going to do. That's how you inflate something. A friend of mine took a job that I turned down because I thought these guys are insane. He took a job he took it with full knowledge of what I told him, but for him it was convenient. He could walk to work, whereas that wasn't a consideration from my perspective. And I remember we had a chat about this after a while, because I said, I just don't see how they could do something, why they need that many people. A couple of years on, he said, yeah, it's kind of interesting. We discovered another part of the organization, in another part of the UK, had developed a system that was functionally equivalent to ours. We took 100 people and about 3 years. These guys took 10 people and about 12 months. We make a system as large, not as it needs to be, but as large as we wanted to make it, because of the way we staff it, the way we create the communication parts. So it turns out that the structures will have a really important force on the software architecture. It turns out this is related to development process and the details within it. Now, I've just mentioned organizational structures, teams, and things like that, and I'm rather fond of a more agile way of thinking. And we can date back a lot of really important agile ideas to not the 1970s, actually, but the early 90s is where they really started becoming maturing, but not yet acquired a sort of fully fledged status. In this book, Pattern Languages of Program Design 2, there's a collection of papers of some of the early 1990s design patterns, but not just design patterns, but also team patterns. There's one of my favorite pattern papers was by Ward Cunningham, the guy who invented the wiki, which, by the way, is a non-tree structure. He did that intentionally because he felt that there was an issue with tree-related organizations. Episodes, a pattern language of competitive development. Here, he was not talking about organizing your objects for callbacks and things like that. He was talking about patterns of successful development. And he had this whole big relationship drawn out. Tasks, agents, who's involved, how the work is distributed, the relationship between these various patterns. And if you're kind of into, from a historical point of view, absolutely fascinating. You kind of see a number of the practices that made their way into extreme programming and therefore had a very strong influence on how we think about agile development. You see the pair programming stuff. You can kind of see the ideas of tests moving their way in and how development builds. The term continuous integration I don't think occurs here, but it's all kind of implied in how this works. And as you can see, this is a mess. It is not hierarchical and tidy. If you were to present a process model to higher-ups, your process model, the chances are, if you were doing this in PowerPoint, you'd try and keep it nice and tree-like, nice and structured and recursive and everything nested and beautiful. And there'd be this beautiful structure where everything broke down into smaller responsibilities. And it would be, I guess, safe, scalable agile framework, which has exactly this structure. But what we were seeing here is the relationship between practices is inherently messy because it's not a software architecture, it's a people way of doing stuff. And it has subtlety and complexity at this level. So he makes this observation. In simplicity of structure, the tree is comparable to the compulsive desire for neatness and order that insists that candlesticks on a mantelpiece be perfectly straight and perfectly symmetrical about the center. I'm going to confess at this point, that's me. And it's probably some of you as well. It's probably one of the reasons we got into coding, because you can make it just so. But it turns out that you don't want that everywhere. And sometimes our efforts to do this backfire. My favorite one, I'll cover very briefly here because I'm going to spend a bit more time talking about it in my talk tomorrow, Programming with Guts, is how we might go about testing. We have a simple model. We might say, I have a function. My function takes inputs, it has outputs. I wish to test it, therefore I write a test case. The problem is we discover that this test case is an absolute nightmare because it has to handle different cases. But it turns out it's not a test case. Your cases of usage are all bundled into this mess. So we decide we're going to partition it. And if you tilt your head this way, not that way, because that's the wrong kind of tree, this way you get a tree. It's nice and simple. And we say, look, I have multiple tests on this. So that's the first innovation, is to go from a one-to-one to a tree. So we have a sophistication there. This is good. This is not a bad thing. It's a good thing. The problem comes when we try to scale it and say, look, I have a class. We have object instances that have multiple methods. And we go, oh, look, we'll have a one-for-one relationship between our test case and our method. And somebody comes along and says, no, 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 you don't want that. And you realize, aha, I need little trees. No, unfortunately, actually, it ends up looking like this. And that's not a bad thing. It turns out that in order to test the behavior of an object, you have to use it. And your usage is not confined in this strict tree-like manner. You cannot just test a method. You have to use other methods in order to test it, either to achieve the state that you want or to query the state that you want. It's a usage scenario you're walking through. We can see this also applies when people try to do one-to-one relationships with classes. I have a class. I'm going to write tests against it. Again, it turns out that a one-to-one relationship between class and test fixture is also not a desirable thing. I mean, it looks tidy, and when you look at it from a version control point of view, and you look at it in your directories, you look at that and go, oh, that's easy. I can see the relationship. The problem is you can't really see the relationship. You're hiding some of the real stuff that goes on, some of the subtlety and actual complexity. It needs to look like this. We see it when people go and try a very simplified version, a non-architectural view of kind of story-driven development or use case-driven development. We start off with a use case, a piece of behavior. Maybe we start off with a set of scenarios we're going to test. And so we build a big slab of code. Okay? You end up with this big chunk of code. And it's the fat controller problem. Okay? You end up with everything's in the controller. You've got no domain model whatsoever. But you know what? It turns out you can achieve incredible velocity in the early sprints of a project just by doing this. We'll do another story. another slab of code, another story, another slab of code. And then things start to slow down because it turns out they have some commonality between them. And copy and paste turns out not to be the best way of creating an architecture. Notice I didn't say copy and paste is not the way to create an architecture. Oh, you can create an architecture like that. It's just not the best way of doing it. So perhaps you have a late realization that things can be shared and factored out. So you factor out commonality. And sometimes people stop there. But there's the idea of, no, I can go further. I can actually go in here and not just look at it from the point of view of commonality, but look at it as a mode of description. That's what you're doing. You're describing something. It is a fiction, but it is an executable fiction. The code is going to run. So you decide to organize things, and you'll notice that we lose the tree structure very, very rapidly. So this is this observation that we often start off with a whole. We decompose it again. We make it all nice, we make it small, we factor out things. It's easy to understand. I'm not going to say that's a bad thing to do. I'm just going to say it's the starting point, because what you eventually end up with, if you look carefully, is this. And there is this question, when we look at this, that the complexity that we have, what we'd like is that this reflects a complexity that is useful and effective in the system rather than accidental, that somehow it reflects the essence rather than the accident. As he observes, the semi-lattice by comparison is the structure of a complex fabric. It is the structure of living things, of great paintings and symphonies. And there is this idea that we want to breathe a little bit of life and a little bit of wonder, if you like, into the code, rather than the normal sense of wonder that you get when you look at a legacy system is, I wonder why they did it this way, yeah? You want a more positive sense of wonder. So, close with this very simple observation. If you're looking for a term that allows you to describe this, Douglas Hofstadter used it extensively in his classic Gödel, Escher, Bach, when he talked about this idea of a heterarchy, a program which has such a structure in which there is no single highest level, and furthermore does not have this kind of strict decomposition. It's called heterarchy, as distinguished from a hierarchy. Hopefully that is food for thought. I'm around all week, and I believe I'm handing over to Alan at this point, so thank you very much. I want to be associated with people who do programs, okay? I'm sure they're lovely people. No, I'm not. I can't do this on a Tuesday. I'm going to be candid and honest. And so, therefore, I think that we should be quite honest. The act is programming. Programming is not merely the act of coding. It is also the act of everything else to do with it. It is the thought, it is the overall architecture, it is the understanding of requirements, it's working with other people, and so on. And all of these things connect to create a structure. And what kinds of structures do we like to use? And what do we prefer and refer to? So I'm going to quote from Fred Brooks' The Mythical Man Month, where he makes a particular observation about how we spend our time. And the first observation he makes, he goes back to Aristotle. Let us examine software's difficulties. Following Aristotle, I divide them into essence, the difficulties inherent in the nature of software. To be precise, the difficulties inherent in the nature of the domain that you are trying to work in. Recommendations for how they should consider their architecture. And I said, the first one, you've got 12 months, you said, to develop this. If you take the first recommendation, it's kind of like a sort of dungeon game, isn't it? If you take the first door, it will take you 3 months. If you take the second door, it will take you 6 weeks, and then you can go on holiday for the rest of the year. But if you choose the door of darkness, as your current estimates and architecture suggest, it will take you 12 months. No, it won't. It'll take you 18 months. They chose the third door. And so every time I go back, in fact, last week was very easy, because I said, didn't I tell you guys this last year? Didn't the problem that you had last year, couldn't you have solved? And it's a little bit like that. So for that team, I can say pretty much everything they have done since 2011 has been to do with the accidents. Now, not all teams are as extreme as that. I saw a couple of really good teams last week. But there is this question of being able to see the structure, to see the trees for the wood, so to speak. Now, you know, pop reference, Michael Jackson. Okay, not that Michael Jackson, a different one. Software and accidents. those difficulties that today attend its production, but that are not inherent. In other words, the things that are not intrinsically a part of the software development that you're doing, that are not intrinsically to do with whatever domain that you're working in. And then the question, to which I think we probably know the answer, unfortunately. How much of what software engineers now do is still devoted to the accidental as opposed to the essential? How much is to do with byproducts of just the way we have designed something, just because we've chosen something in a particular way? Now, I was doing a consultancy visit last week to a company, and I saw a couple of their, let me think, four of their projects. And I've been doing stuff for these guys for a number of years. So there's a lot of continuity there. And one particular group, it's not that I kind of hit my head against the wall every time I see them, or burst out into uncontrollable tears or anything like that, or run fleeing from the building. But it is one of those things that a few years ago I gave them two recommendations, and then look at what we mean by, well, a system is not a tree. What does that actually mean in terms of how we code and how we reason about systems? It would help if I turn that one on. There you go, the power of on. Yeah, brilliant. Let me think. Why have I put this here? I put this here because my name's on the cover of them. I put this here also because it happens to summarize a couple of areas of interest of mine, and one of the aspects of patterns will come up later. Architecture we think of as being the gross structure of a system. There's a bit more to it than that, but there is this idea of this large concept of the system. And then we break it down, and we break it down all the way to the stuff that we talk about when we talk about programming. And I'm one of those people who actually quite likes the word programmer. Software developer seems far too many syllables, and if you shorten it to developer, then you can get into those interesting conversations with people. What do you do? I'm a developer. Oh, yeah, my partner's in real estate as well. And that's not really a group of people I want to be associated with. Good morning. So, a system is not a tree. That's a bold assertion. I want to talk about structure. Structure in the abstract sense, because that is what software is, structure in the abstract sense. It's not concrete in the way that most things are in a real-world sense, and indeed, it's not living in the way that something like a tree is. The question is, what is it that we do when we organize stuff? If you like, a software system is organized thought. It is executable fiction. It's stuff that we make up, but we give it some kind of structure. It's not just arbitrary. Well, actually, you may have worked on a system where it feels kind of arbitrary. But it's not supposed to be arbitrary. It's supposed to have some kind of discernible order to it. It's supposed to be comprehensible. It's supposed to be a reflection of the thought stuff, but with a little bit of consideration. And so I want to go through what we mean by, when we say a system is a